Good morning. Welcome to NPTEL course Transfer Phenomena in Bioprocess Engineering Week 4, Lecture 2. So, today we will discuss about the NPSH and then cavitation. So, what are the concepts and how to prevention the strategy we will discuss today class. So, what is the cavitation? So, the cavitation is the localized evaporation of liquid or the rupture of the fluid solid interface caused by a drop in the local static pressure. That is the local static pressure is the it's a below the fluid's vapor pressure, or we call it as a saturation. The PV stands vapor pressure and the PSAT is the saturation pressure, but it works at certain operating temperatures, not like varying temperature here. At certain operating temperature it works here. So, while both boiling and cavitation both involves the liquid and vapor phase transition, of course we know boiling is the driven by the increase in the temperature. Whenever get increase the temperature, there is a boiling will always be there, but whereas the cavitation where will there always it is driven purely by a reduction in the static pressure due to dynamic of the fluid oscillation. Then cavitation, so impellers use a 3-stage of physical mechanism. So, there is a 3 stages there, the physical mechanism. So, what are the 3 stages are here? The phase 1 vaporization or nucleation. So, as the fluid accelerate into a low pressure section of eye of the pump impeller, a local static pressure falls below the vapor pressure. Always we are talking about the vapor pressure, it is a below of the vapor pressure, allowing so entrained this gas or voids to rapidly expand into the visible vapor bubbles. So, there is a cavitation of bubbles are there, that is called cavitation of bubbles. Then the phase 2 is the transport, how we are transport this one. Then again the flowing steam that transport these vapors whatever the cavities to the downstream area of the increased static pressure along with impeller blades. Then phase 3 is the collapse, get collapse here. When the surrounding of the fluid pressure is too high, is very high, then automatically the vapor bubbles gets collapse, then releasing the localized pressure, it gets spikes, then microjets, micro scale shock waves all be there. So, totally the 3 stage of physical mechanism. The one is the phase 1, phase 2, phase 3. The phase 1 is the vaporization part, there is a nucleation part. Then phase 2, how the transportation from here, that is a transport of that one. Then the phase 3 will talk about the collapse, how the vapor bubbles get the collapse due to the pressure of this one. So, then if you want cavitation, the collapse of the bubbles of course is undesirable. So, what are the it can cause the following. First, definitely it produces the noise. So, whenever the bubble gets collapse, it gives for noise. Then it's a vibration of also there, the vibration is also there. So, whenever get the bubble get collapse, the efficiency of this one definitely get decrease. The whatever you are expecting the efficiency of the process definitely we get the decrease, that is called reduced efficiency. Of course, definitely this will damage the impeller blades, there is a blades are there. So, if it definitely get the damage of the impeller blades, or sometime erosion of the blades and eventually some blade failure also will be there. And the last point is the cavity formation decreases the total dynamic head produced by the pumps and then greatly reduce the mechanical efficiency. So, definitely whenever the bubbles get collapse, the efficiency of definitely will get decreased, that is the main point. And if of course it gets the damage to the impeller blades, it give lot of vibration, noise all together. So, then what are the types of cavitation? So, there is a vaporous cavitation, then other one is a gaseous cavitation. The vaporous cavitation occurs the degas liquids when normally the static pressure gets drops below the vapor pressure then it generates the explosive, highly destructive vapor bubbles get collapses. That's called vaporous cavitation. So other one is for gaseous cavitation. The two type of cavitation here. It occurs higher static pressure. It occurs the higher static pressure when the dissolved entrained air or gases released from the solution act as a cavitation nuclei. So what we have to do for this to avoid the cavitation, because cavitation of course we have to avoid. To avoid the cavitation, we definitely must guarantee that the local pressure of the inside of the pumps remains higher than the vapor pressure. So the whatever the local pressure, the inside the pump, it should remain always higher than the whatever already the vapor pressure. So the cavitation criteria usually define the pump input of, since the pressure is very easy to measure because so many instruments are there to measure the pressure. It's a very easy to measure, so that this point is very important. So the type of cavitation is, one is a vaporous cavitation and then another one is a gaseous cavitation. So here wherever the static pressure drops below the vapor pressure, then automatically this will occur. Other one is it occurs a higher the static pressure. Whatever the static pressure higher, then this will dissolve the entrained gases released from the solution act as a cavitation nuclei. So the next is net positive suction head. So we always write NPSH, that's called net positive suction head. So what is net positive suction head here? Is the pressure or head of the liquid required to prevent the cavitation. Because you want to prevent the cavitation, of course we need NPSH, that's called net positive suction head. So NPSH is the pressure required at the pump inlet. That's where is the inlet now, that is where we are pumping the pump inlet there to prevent the fluid from vaporizing, that one. Of course it measures the pressure of the liquid at inlet of the pump to ensure it remains as a liquid and does not flash into the vapor bubbles, does not flash or boil the vapor bubbles. Of course, it is a measurement of pressure experienced by the fluid on a suction side of pump. There is a suction side of pump is there, and calculate as the absolute pressure minus the vapor pressure. So here you can see net positive suction head, NPSH. We always write net positive suction head. So there is a P by rho G. The P by rho G is the pressure energy. We already so many times we discussed the P by rho G. There is a Bernoulli equation. So three types of energy together. There is a pressure energy, then kinetic energy, then potential energy. So here this is a pressure energy P by rho G, then V square by 2, that is the kinetic energy, V square by 2. There is a G, G is the gravitational, that one. So the pump index there. So minus of vapor pressure, the PV stands vapor pressure. What is the vapor pressure? And this is the absolute pressure, whatever the pressure here. So basically is a minus between absolute pressure and vapor pressure. This is also called a pressure energy, but called a vapor pressure energy. There is a PV by rho G. So the net positive section is the two key types of NPSH, that's a very important. So one is called NPSH available, net positive suction head available. Another one is called net positive suction head required. So there is available here the actual pressure of the head provided by the system in the piping or tank setup. So normally what available for that one. So then other is for required here, required the minimum pressure head needed to the pump by to prevent the fluid from flashing into the vapors. So normally these values normally specified by the pump manufacturer. So whenever they are giving pump, the manufacturer itself they used to give that values. So there is a two values there, NPSH available, then NPSH required. Okay. So these are two very important key types of the net positive suction head here. So what is net positive suction head available here? So, we have to see what is the difference between this one. So, the net positive suction head available is the actual pressure head available the pump suction, there is a suction point, no, that point that exceed the liquid vapor pressure. So, it is always relation between the pump suction then liquid vapor pressure. So, that point exactly how much of the actual pressure available at the pump where the suction taking place, no, that exceed the vapor pressure. It always gives the pressure required to maintain the liquid in the liquid phase before it enters the pump. So, it describes how much the pressure required to maintain the liquid in the liquid phase when they entering liquid phase, no, before it enters the pumps. So, then what are the physical significance of NPSH available? The physical significance here, it indicates the pumping system, whatever the pumping system, whether it is the ability to prevent the vaporization, whether it is the ability to prevent the vaporization. The second point, it depends on the suction piping system, not in the pump. The third one is always NPSHA available. We have NPSHA, that's called available, is a higher. Whenever NPSH available higher, then definitely the cavitation will be the probability is very, very low. So, that is the main point here. NPSH available, if it is higher, whatever the values, the required value, then definitely it is the lowest the probability of cavitation. The cavitation part will come as a very, very low. So, then there is a apply Bernoulli equation, the NPSH available here. We already discussed the week 3. So, what is the Bernoulli equation here? The Bernoulli equation between the liquid surface in the suction tank. Where is the suction tank here? Liquid surface suction tank, point 1. Then the point 2 is we called as a point 1, point 2. Normally Bernoulli equation we always write like this, because there is what is the pressure energy and what is the kinetic energy and what about potential energy at point number 1. At point 2, what is the potential energy, then kinetic energy, then pressure energy. So, here at point 1, there is a pressure energy P1 by rho g, we always write a pressure energy here. Then Z1 is a potential energy. So, that is equal to P2 by rho g, that is a pressure energy at point 2, that is called a pressure energy at point 2, P2 by rho g. Then V2 square by 2g is the kinetic energy of this one. So, there is Z2 again potential energy here, it is a pressure energy, then it is a kinetic energy, then it is a potential energy, and HF is the here friction loss in the suction line. So, all they mentioned here. So, finally, the NPSHA, the net positive suction head available, the pressure PS suction, that is the absolute pressure at suction tank PS. Then Vs is here velocity of liquid at pump section, the Vs here. So, Hs we use the static suction head, Hs the static suction head here. Then the PV is the vapor pressure of the liquid, PV is the vapor pressure of liquid. Then the HF here, the friction losses in the suction line. What is the friction loss in the suction line? So, this is a net positive suction head available here. So, the NPSH available, so this equation we can always get. So, wherever if you want net positive and available, use all the values and we can get the value of net positive suction head available. So, net positive suction head available only mainly depends on flow rate of the system. So, what is the flow rate? If flow rate is high and flow rate is low or medium, so there is only the depend on the flow rate. Then what the liquid temperature is important. What temperature we are using, that liquid temperature is another very important. Then vapor pressure of the liquid, the Vp, we write Vp, vapor pressure of the liquid or PV, okay, vapor pressure of liquid. Then suction piping losses, that also we are counting that one. What is the suction pipe losses here? Then atmospheric pressure. So, these are the net phosphate section available, mainly flow rate, then the liquid, what is the liquid temperature, then vapor pressure of the liquid, what is the vapor pressure of liquid we are using here, then because there is a difference between vapor pressure, then suction pressure, all we have to take that one. Then suction piping losses, what are the friction losses, that also we have to count here. Of course, finally, the what is the atmospheric pressure, that is very important here. So, if you want the net positive section head available, it is mainly depend on these are the variables. Then what is the strategy to increase the NPS available? So, how to we can get increase the strategy, the net positive section head available? Of course, only we can increase the liquid level above the pump. So, where there is a pump is there, but always you can increase the liquid level wherever the pump installed, you can always increase the liquid level, then such a way that we can increase the NPSH available here. So, other point is reduce the suction pipe friction losses. So, you want to increase the NPSH, what we have to do? The previous time we discussed about the variable, but here how to increase the NPSH available. So, reduce the suction pipe friction losses. If you want to get reduce the pipe losses, friction losses, then automatically the NPSH available get increase. And then use a larger suction pipe, use the larger suction pipe, then minimize there is a lot of bends, then we will use lot of walls. So, try to minimize the bends, then walls. Of course, the temperature is also main part of that one, you reduce the liquid temperature. So, you want to get NPSH to increase, we have to follow the strategy of first is you have to increase the liquid level, then of course, you have to reduce the suction pipe friction losses, otherwise you use larger suction pipe, then minimize the bend, then finally of course, you have to reduce the temperature, then we always get the NPS available is to get the increased chances are there. So, here the net positive suction head require here NPSHR, there is here the figure given very nicely here, the NPSHR, there is a NPSHR. So, it is a required, we discussed all previously what available. Now, net positive section required is the minimum pressure head required at the pump inlet to prevent the cavitation of inside the pump. Of course, we need always cavitation occurs, to try to avoid we need a minimum pressure head, we need that one. Unlike the net position available, the NPSHR characteristics of the pump determined experimentally by the manufacturer. So, NPSHR always the manufacturer there, no, they always give that value of net positive suction head required, they always give that values whenever the pump this one. So, the measured value of net positive suction head required, that is a required, the previous one is available. Availability is always high, then of course, our cavitation part will get decrease. So, the net positive suction head required varies with the volumetric fluid, it should vary with this one. So, there is a head is here and there is a volumetric flow rate. You can see here when you increase the volumetric flow rate here, automatically the head get decrease, but the net positive suction head no, NPSH value, NPSH required, it is always get increase the values, is getting increase if you increase the volumetric fluid. That is we often plotted the same pump performance curve as a net head, because there is a net head is a y axis, then x is the volumetric flow rate, and if you want head always get drop that one, but the required get increases when you increase the volumetric flow rate, that is only they given the graph. So, now the pump function efficiently, you want to pump the function efficiently when energy is available higher than the energy required. So, this available always higher to records, then only the pump works the efficient way. Why this condition is very important? Because if available more, then the prevent the vapor bubble formation at the pump inlet, because whenever it's very high, then the vapor bubble formation at the pump inlet definitely that prevents that one. Then avoids the cavitation inside the impeller. There is an impeller inside, you try to avoid, because if NPSH A available higher, avoid the cavitation inside the impeller. Then ensure the stable pump performance and efficiency, because you want to get a good efficiency and good performance, but then net positive section head available should be higher than the net positive section head required. And always protect the impellers, then bearings, then mechanical seals from the damage. If NPSH A is available is higher than the required here. Once again repeat, because it definitely the why important, it prevent the bubble formation, then definitely avoid the cavitation, of course ensure the stable performance and efficiency also. It always protect the impeller and then all other mechanical seals from the damage. So then NPSH required here, when expressed properly in unit head of the liquid being pumped, NPS record is independent of the type of the fluids. What type of fluid you are using, that doesn't matter, it's independent of the type of the fluids. So what are the characteristics here? It depends on the pump design, how you are design the pump, that is a very important. It varies with the flow rate. Whenever the flow rate get this one, it's always varies the flow rate here. It always specified in the pump performance curve. It is specified in the there itself, the pump performance curve NPSH required, always they will mention in the pump itself. It cannot be calculated directly from the piping system. We cannot calculate from the piping system. It's always the manufacturer itself used to give the value of NPSH required. So this is very the figure given very neatly here. So what is the NPSH required here? See, as the flow rate get increase, whenever the flow rate get increase, the velocity of the liquid in the suction pipe also get increased. Because whenever the flow rate increases, this is a flow rate and then suction head, the flow rate get increases, the velocity of liquid in the suction pipe also get increases. And this leads to what are the problems here? Higher frictional head loss, that's a HF, the loss always very high than the lower suction pressure at the pump inlet. The pump inlet, the lower suction pressure here. It's a decrease the NPS available. If this leads, automatically it get the decrease the net positive suction head available. At the same time, what happened at the same time, the pump requires at the higher inlet pressure to avoid a cavitation. Because if it get decreases automatically, then the pump definitely need more higher inlet pressure to avoid the cavitation. Therefore, the NPSH record increases with increasing the flow rate. So finally get increases. You can see here the graph here, this is a volumetric flow rate. So volumetric flow rate here and other part is the head that getting decrease here. So one is a net positive section head available, NPSH is available A, then other one is for NPSH required. One is NPSH available, then NPSH, another is the required here. So whenever the required get increase, you can see here whenever get increase, then automatically the cavitation also, the available get decrease, but required get increases, then cavitation starting. Whenever available is very high, there is a no cavitation this side, because the NPS wherever available, then there is no cavitation, but whenever NPSH required is increasing with respect to volumetric fluid, then there is a cavitation is there. Here the graph is explained that one. Okay, so now how we have to industry operation we have to do. For any reliable industrial operation, we have to maintain the safety margin. That's a net positive section head. Of course, always net positive suction head available is greater than the required or equal or greater than required, but there is a safety margin also there to run the system. So, normally 10 to 20% or 0.5 to 1 meter. So, basically on what are the application we are doing, that depending on the application is commonly recommended. So, the safety margin also there, that's some points, that some additional the values are there, then required is there. So, net positive suction head available always the greater than the required. Of course, some safety margin also we have added here. So, the problem 1 we will discuss. The water at 40 degree stored in the open tank atmospheric pressure, that is at open tank and the water temperature is a 40 degree. The pump is 2.5 centimeter above the tank level. Where the pump is there, but the above the tank level they kept that one. The velocity of pipeline is 1 point. Velocity of pipeline is 1 point. The friction head loss the pipe they calculated. The friction head loss here 0.8. HF is a 0.8. So, the required NPSH R is the for the pump 2.5 meter. So, NPSH R value also there. NPSH or required value also there, that is a 2.5 meter also given. Of course, density of water, then what is the atmospheric pressure, then vapor pressure, but they are asking what is the calculate the value of NPSH available. They are asking the available, what is available here. So, all values are given here. So, this we always use the net positive suction head available. We already discussed. So, there is a P1 by rho g atmospheric pressure, then V square by 2g. There is a kinetic energy, it starts with the kinetic energy. Then PV is the vapor pressure of water. What is the vapor pressure of water here? Then HF is the friction loss. HF is the friction loss. So, all values are already given, just you calculate and substitute, then we get the value of NPSH here. So, what is the P1 here? Atmospheric pressure. So, there is a P1 by rho, there is a G also there. Either you can take G here or here, whatever there. Okay, G is the 9.8 values. So, P1 by rho, then 102.12 meter. Then vapor pressure head, that is a PV by rho. Another is a vapor pressure head, PV by rho. You calculate that one, we got 7.44 meter. So, this is done, then PV by rho also done. Then V square by calculate the velocity head, that is a velocity head. From there we calculated 0.72 meter. So, then the static suction head they already given the problem. They are saying that 2.5, you can see here the pump is 2.5 centimeter of above the open tank level. So, that is the 2.5 meter the tank level above. So, then it is a minus value here. So, then G is at 1, first one calculate, G is the 9.8, the Z1 is the 2.5, we calculate the value of this one. Same way for friction loss, GHF, then 7.85. So, we know all values, this is the equation, we know HF and we know this velocity head, then we know kinetic energy, then we know vapor pressure here, then the atmospheric pressure, all values we know. So, substitute all values here, then the G of NPSH is available here, you just substitute all the values, then finally we get the NPS available, this value is the 6.28 meter. So, already the given problem 2.5 meter, it is above the value. So, then our pump will operate the safely without any cavitation. Then the problem number 2, the same problem, a feed rate is a 300 gram per minute, the 300 gram per minute, the hydrocarbon mixture at 60 degree, there is a 60 degree temperature is being pumped from the tank at 1 atmospheric pressure, the distillation tower, the density of feed is there, then vapor pressure is there, the velocity, the inlet pipeline, the velocity also available, then the friction loss between the tank and pump HF value 2.5 feet of, this all are not in the SI units, whatever unit we can use it, otherwise you want to convert, you can convert in terms of SI units. The net positive suction head required is NPS required is 8 feet. So, there are what the question is here, how far the below the liquid level in the tank must the pump to be obtained the required net positive suction head required here. So, what is the feed? It's a boiling point. If you keep a boiling point, what is the calculate the pump position? So, these are given values, atmospheric pressure, vapor pressure, the density, all in terms of all British units here. So, then 4 feet for this one, velocity, friction loss. So, what is the required NPSH here? Then gravity. But what they are asking here, so what is how far the liquid? Then second one is, if the feed is a boiling point, calculate the pump position. Of course, this we know already, this equation, we know that one. So, this is a gamma, this rho g value 50 lb force per feet cube. You substitute the PS minus PB because we know the value already, get the value of that one. So, there is a pressure head, the PS value is a 14 point, this one PS value. So, you convert in terms of this one. So, PS is here, the PS minus PB, the value 1137, then divided by density, I mean the gamma here, we always this one, then 22.75 feet, that is a meter, 1 feet equal to 0.305 meter here. So, then next you calculate the velocity head, then of course, you know all the values, just substitute the net positive suction head available required is already the problem itself 8 feet already given. So, from there we can calculate the HS value here, what is the pipe loss here. So, since the value is a negative, the pump can be installed 12 feet above the liquid level because the negative is there. So, then automatically we have to install the pump above the liquid level. If its boiling point both are same, that the PS equal to PB, the vapor pressure equal to this one, then automatically this get 0, then we have to calculate, then there is a height is, this is HS is the 10.75 feet. So, it's a positive value, then it should be a below the liquid level to avoid the cavitation. Basically, where we want to put our keep our this one. So, whether below or above to avoid the cavitation. Thank you.